Hello, everyone, and welcome to Handmade Hero, where we code a complete game live on stream. We finished up last week with all of the code in place, but we haven't had a chance to really work through it and make sure that we've actually got anything working correctly. So we've definitely got a bunch of debugging work to do this weekend. And when I say debugging work, I kind of mean two things. One, I mean like the actual act of debugging to fix problems in the code. But also because we've done such a wide swath of stuff, like we basically completely replaced the ray tracer and how it works almost completely. Like every last bit of it is different now. We also kind of want to spend a little bit more time stepping through it just for our own like educational purposes. When you write a bunch of code like that and you're like, okay, here's how each piece is going to work, and you do a whole replacement, and now you've got different things happening at each stage of the process that you had than what you had originally, it's pretty easy to miss a few things or to think something's working one way, but it's actually not working that way and it's working another way. And you may have forgotten, especially when you're doing stuff like when we are, where it's every week we program for 4 hours or something. It's not like we did this all in one day, right? And so what we really need to do is we need to make sure that, A, we understand that everything's happening, that we understand how everything's happening, and we're not like missing some crucial things or failed to take advantage of certain synergy that would have been like brought about by these changes that we can then leverage in other parts of the code because we didn't really think of it, or whatever, because we weren't paying attention to that part at that particular moment. And then we also need to get the basic flow correct, so any bugs that are happening, because we just we put a lot of this code is very performance critical and it's very like tweaky, right? It's like, okay, we're doing all these crazy bit manipulation things and we're trying to make everything run as efficiently as possible, so everything is a little bit delicate as a result. It's not as simple as it could be. It's more complex due to the performance concerns. So everything's got to be happening wide, and we have all kinds of like things where we're trying to minimize the number of operations we're doing, so we're not doing things in the most verbose way possible, and so on. So all of those things also kind of combine, right? I don't know what is the. I don't know what that is. So we basically need to do all of that process. So let's go ahead and see if we can't get started on that process today, and just sort of like get through a little bit of that sort of slow process of just like making everything work properly and making sure that we understand it. So let's start with a walkthrough of how the code is now supposed to work, which again is a little bit different than it was working before. So what we intend to do now is, in addition to building a texture, like two textures really, but as far as the raycast is concerned, we're talking primarily about one particular texture, which is the diffuse texture that we sample from, although we do write back into the specular one, so both are in play. So in addition to the voxels that these textures represent, because each texture represents a voxelization of the world, I believe it's like 24 by 16 by 16 or something like this right now. I don't actually remember what it is, but it's 24 by 16 by 16. So I take it back. I do remember what it is, I guess. So each one of those textures represents a voxelization of the world, and each place in that voxel records an octahedral map that is the lighting, either the specular or the diffuse lighting. The specular is what we actually compute, because specular is what happens along rays. The diffuse is something we generate from the specular, and that's just a way of basically convolving the specular map into something that has the sort of cosine reflectance fall off that you would expect from a diffuse surface. So when we get to that point, we then say, all right, we need to be able to trace rays. And so what we're doing here is we're saying we need to go through all of the actual locations in our voxel. We need to cast rays out along the directions of the octahedral map. And because we want to cover the whole area of the octahedral map, since we don't really have a way of ray casting into the world and collecting all the light in an actual like frustum that would be implied by being able to cast out from the octahedral map, what we do is we point sample it with rays and each frame we cast a different direction out of each place in the octahedral map so that we hope we cover the map in general. So this is the loop that does one slice, a YZ slice, and we distribute X slices, of which there are 24, across all the threads we have. So, in a perfect world, we'd have 24 threads, each one doing a different slice, and if you happen to run this on like a thread ripper or something, that's exactly what would happen. But on most machines, especially like Intel machines, where they have a really hard time getting the core count up because they didn't go to multiple chips on one substrate approaches early enough, you only have, say, 8 cores to deal with most of the time, sometimes only 4. And so what we're actually doing is we're probably having each thread do several of these X slices in series. So a thread will basically wake up at the lighting time. It will start chewing through the list of work units that it needs to process, and each work unit will be one of these slices. It's an entire slice rather than a single voxel cell, just because we don't really want to spend a huge amount of time banging on that queue. It's a single queue, and you can't really have lots of threads banging on a single queue often. If you do, you will simply lock up the threads waiting for the queue mutex or the cache line if it's lock free. So again, it's just worth thinking about this as you get more into multi-threaded programming. It's just worth understanding what's going on there. There's a single work queue, and all of the threads just pull the work off that queue. That's a model that only works when the work is heavyweight. If there isn't a lot of work to do on each work unit that you pull off, this would be a horrible design because everyone would just lock up in order waiting for that cache line to become unexclusive. And so, this is just not a structure you would be doing for that. So that's why we have a fairly large work unit. If we wanted to start to generate a more granular approach to something like this, we would do it differently. So as we come through here, we're pulling off entire slices. And what we need to do here is we then need to say, okay, where actually in our grid is this particular starting point? Because we're going to cast out of the center of these cells, and we need to know where the starting point is. So we create this thing called the initial grid index. And what that is it says, all right, in addition to the voxel itself, which is the textures themselves, which is what we're writing and retrieving light data from, we also are going to have a spatial partition. And because of constraints on the way that we're walking the spatial partition and the fact that we don't want to go outside of it, not so much because of fetching out of bounds, because we could easily protect against that, but more just because we'd get incorrect results when we wrap around the voxel. What we've done instead is we've said, let's make a slightly larger voxel, and this slightly larger voxel will have a 1 voxel cell apron around the outside that is just there to show you that you've walked outside it. And that way our actual voxel casting routine can just go ahead and have a simple exit criteria. So what we do is we create an initial grid index that says, okay, let's take the voxel dimension with the apron, which is that sort of extra piece that goes around it, and let's go ahead and see where we'd be in there. And of course, we have to have +1 on each of our coordinates because this thing has a 1 wide apron. So if you want to be in a specific cell, it's going to be +1 in all the dimensions to account for that apron, as compared to the one that doesn't have the apron, which is the way we're storing our textures. And of course, the textures don't need an apron because they never it's sized to the screen such that you never sample outside it anyway. So we don't really have to worry about that. And if you were to sample outside it, we wouldn't care. You could just return whatever the closest one was, and it would be fine. So we have that set up, and we create this initial grid index. We then go through and say, all right, there's a should compute here, which is if we want to turn on sort of like a checkerboard-based tiling to reduce the computation cost by further reducing the frequency of updates that we do, we can. We don't have that enabled right now, but we may want to enable that, especially on slower machines with less cores, things like that. So we leave that in there for now because we're not sure what we want to do with it. We then go through and we have some test code here that we can do, like this test sphere and so on, that we were using for testing lighting, but really we don't do that anymore. It's just sort of a vestigial remain that we don't maybe want to pull out just yet because we're still not quite sure we've got everything nailed down, but we've got the test sphere in there, but what we're really calling mostly is the full cast call. The full cast call is what does the actual ray tracing for a given octahedral cell, so that's what we're going to be looking at primarily. We then go on to this diffuse tile bit here where we take the diffuse texture and we write to it. So you can see here we're writing to the diffuse texture, and this is our single update step. It's the only time we actually update the diffuse texture. Normally what we're doing is we're actually updating the spec texture, because the specular texture is what records the result of raycast. It's the thing that records the thing you see directly out in a line, and that's what we can determine with raycasting. We really have no idea when we do raycasting. That doesn't give us any information about the diffuse reflectance in an area, because diffuse reflectance is going to be blurred, right? It's going to be a summation of lots of specular casts. So we compute the specular casts, and then we produce a diffuse map by averaging specs, the specular cast that we've done, and we average those using cosine weighted falloff, and that's what this routine, well, not really routine, this is what this loop here will do. We then fill the borders, and those are just there to make sure that we don't have wrapping artifacts. So this is so that when you sample towards the edge of the octahedral map, it properly samples basically around back to the other side, which is what you would want it to do because, you know, this is supposed to cover a spherical region. It doesn't have any actual seams. So that's to hide those seams. So we don't really care about this part of the code right now. In fact, we may change the way this part of the code works later. It's totally separate from the raycasting part, but that's what happens here, right? So all of that is probably working properly. The only part that we've changed recently is this initial grid index to something that we added. That could easily be a mistake or something wrong happening there, but the rest of this code is the same for regardless of which raycast transport you tend to use. And we know it was working fine with the old one, or at least it seemed to be working fine, meaning there were no visible errors with it. So we wouldn't expect there to be visible errors with this one either if the raycast is working properly. So really what we're looking at, although this initial grid index is something that we do have to take a look at and make sure that we're working with properly, other than that one line, everything else in this function could probably assume to be working well enough at the moment because we know that it worked okay with the previous ray transport. So it's really the full cast routine that now we have to scrutinize, and there's two parts to that. There's what it calls, because it calls this raycast function, and we have the new grid raycast function, which is what we replaced that with. And then we also have the full cast itself. Now, again, the full cast itself is not that suspicious because we know that it really doesn't do anything in particular, but we do have to pay a little bit of attention to how it's working because we have to make sure that things get passed through properly, right? So we have the initial grid index here, and it eventually calls raycast to do its work, and you can see that we've got initial grid index here getting passed through. Everything else gets passed the same regardless of whether you're using the old raycast or the new one. And in general, this particular function will probably want to be modified in the future as we collapse things down. We've got too many layers of cruft at this point, and they're mostly there because of the experimentation. So at some point, we're going to want to collapse these down. Now is not the time to do that because we want to leave all of this sort of goop in place as we sort of work with different systems until we settle on exactly what we're doing. Hopefully that will be soon because hopefully our grid raycaster is actually good and we can just standardize on it and then be done with it. But you know, you never really know when you're doing experimental code and trying to figure out the best way to do something. You don't know ahead of time which answer you're going to end up with. So you can't remove cruft too early because you don't know what is cruft and what is necessary. That's just a basic problem with experimental code. So if we take a look at the raycast call here, you can see what we're doing is normally in the raycast call, we actually kind of do the work here. And this was our old raycaster that's sitting here in place. We actually had multiple versions of it that we tried. We tried a KD stack one, we tried a box stack one. And then right here, we've got sort of if zeroing of them out. And you can see that we sort of have a different version that will actually do a grid raycast instead. And so this is actually the code that we're running now. And all of this code we expect, or I should say we hope, we will just delete. Meaning all of that code that was experimental, us trying to get a good raycaster, you know, hopefully we'll just be able to settle on just this one here. And we will just weld this grid raycast into place at that point. But again, we don't know that. That's just, that's just our hope. That's what we're hoping will happen as we test out the various algorithms. So what you can see in here is what we do is we basically initialize the transfer PPS value, and that's basically the photons per second, which is a rough sort of arbitrary quantity we've defined as the thing we're going to have to measure our light. So it's basically a measure of the rate at which light is going through the system. Inside here where we have the grid raycast, we are saying, look, please write to the transfer PPS for this. So tell us, what you think we are actually getting in terms of red, green, and blue wavelength photons coming back through here. And then we pass in, the basics. We pass in where the origin is for the ray, so where we're casting from, what direction we're casting, what grid index we believe that to be in the table, and then a table that we look up which says how to walk through the actual, how to walk through the grid as we go. In the actual grid raycaster itself, I think we did a pretty good job of keeping it simple. There's not a lot of code here. And so what ends up happening to do a single raycast, there's some initializations to record the values that are in question that we need to use to actually process a hit. There's a shuffle table that we use, which is just what we load constants from, and we use this to actually do broadcasts we use this to do broadcasts. Oh, right, okay. I was like, but why? And then I was like, right, because they're dynamic. So one of the problems that you have when you're writing SSE code, it's kind of a bummer, is just that when you do an SSE dispatch, you don't really have any way of doing any of the normal operations. So shuffles and unpacks and all the things you would normally use to move data around, they can't be dynamic. In other words, when you do a shuffle with the original, say, SSE shuffle or the SSE2 shuffles, those shuffles don't actually allow you to pass in any information. You just have to say, I want to do this particular shuffle, because the shuffle pattern is an immediate that's welded into the instruction. So short of self-modifying code or some other kind of really problem child things you could do there, there'd be no way to say, look, based on, say, a comparison of elements inside one of my vectors, I want to do this particular shuffle pattern. The only way you could do that would be using a branch, right? Would be using a switch statement or something like this, a jump in the assembly code. And so what we've done instead is we've made a shuffle table, because one thing that you can do in SSE, I don't remember if it's SSE 4 or 2, but I think it's 4, maybe 3, is there's a byte shuffle that does take a shuffle input. So basically what it does is it takes takes the 16-byte value to shuffle, register to shuffle, and a 16-byte input that says what to shuffle where. And so you can have a dynamic input with that. And so that's why you see us using that here. It's because we don't have any other way of telling it to shuffle. This is a very simple shuffle. It's a shuffle that could trivially be done with the shuffle with the immediate. The problem is that immediates are welded into the code. If there was something that was simpler, we could have done it. We wouldn't have needed a whole table. Either way, it's not the end of the world. It's one cache line worth of stuff. So, it's not a disaster, but that's why this is happening here. Okay. So what we do is we start out by initializing the shuffle value to whatever the first shuffle is. And the reason for that is because we don't know that we'll ever actually find a hit, and we don't want all of our code at the end to fail if we don't. We start at the grid index that is indicated by our caller, so the grid index that we know we were stepping through, that's where we start. We also initialize a cost metric value and a t-terminate value. These are just there in case we run out of grid to walk, or we feel like we've done too much work and want to stop early. So these are here primarily for early termination. in the event that we actually hit something, we don't need these, but we don't know that we actually will hit something, or we don't know that we'll hit something within the computation budget that we allow. We start by looking at the node that we start in, and that's why grid index is initialized to initial grid index. And what we do is we say, look, if we hit a spatial node terminator, a grid node terminator, that just means we have hit the apron and we don't need to walk anymore because we're just walking out. We've left the grid area. So this is our termination condition for out of bounds. We then look through all of the leaves that exist in this particular location. So we look up the spatial grid leaf table. The spatial grid leaf table just is literally a table that says, excuse me, here are all of the things that exist at particular locations. So another way to think of it would be, it's basically a packed array with all of the boxes that you can hit, all the occluders and the lights as well. And then each of the nodes that we walk just says what chunk of that leaf table to use. So we're looping over that leaf table and we're just pulling out all of the things we might intersect with from there. We're then doing the box intersection, and this code isn't new. It's basically exactly the same as it was before. So the box intersection code has been preserved. It didn't change, because we already thought it was reasonably performant before. We didn't think there was a way we could really make it go particularly faster. So the only thing that we did differently here is we just preserve different values in the case where we do hit. Previously, we've been preserving the box min and box max. Instead, now what we do is we preserve the t value that we thought was the actual hit. And the reason that we're doing this is because this will let us pick out the correct value using our shuffle table later. So that's what's going on there. So as we come through here, you can see that all we're really doing is we're just recording that information, and we also build a mask over time that we can use for a future jump that basically says, did we hit anything at all? So if we did hit something, we know that since we're walking the grid in order, we can early out at that point because we don't need to look any further. If we've already hit something, we can't possibly hit something sooner in a later grid cell. And we ensured that when we built the actual grid, because what we did is we clipped each of the boxes to the grid cell that it's in, and so we know that there isn't any cases where you can go to a future grid cell and get an earlier hit. That's no longer possible. So we look to see whether or not we did hit something, and if we did, we're going to terminate. And the way that we terminate is we first say, all right, we need to look up to see which kind of shuffle we're actually going to do. And you can see here that when we actually do this, to do the, I'm sorry, we don't quite do that yet. That's actually happening here. The first thing we have to do is we have to put all of our data in place to do a horizontal comparison. So the way that we do this is you can see in here we've got our data set up so that we're going to take the 2nd and 3rd, the 6th and 7th, the 10th and 11th, and the 14th and 15th values out, and then we're also going to replicate this to the 2nd and 3rd values into the rest of the table. We're going to do that one shuffle, and what that shuffle is doing is it's taking the highest part of each of our floating point values. So actually, here's a question. Were we overly clever here, though? So if you look at what's happening here, we're trying to extract the minimum value. So, we just want to know which one of these 16-bit values is the lowest, is what we're asking it for. I mean, that's what this is, right? And the thing that I don't quite understand is that we should have to compare the entire floating point value in order to do that, right? I mean, basically, this is just ignoring 16 bits of mantissa. Which, I mean, I guess is maybe you would just say that's okay because we just need to know roughly which one is the closest. But it's a little odd, right? I mean, at the very least, I think we probably needed to do in there because it just doesn't seem... I mean, out of the 32 bits of the floating point value that we're comparing, we're obviously comparing the best part to compare, meaning we're comparing the part that's the exponent and the most significant bits. So, you know, we're comparing like 8 bits of mantissa or something and the exponent. But I'm not sure that is that enough? Like, I don't know that we know if that's enough or not. You know what I mean? Like it may be that those remaining 16 bits of mantissa were important and we don't seem to care about that. And I'm not sure that we actually did the work necessary to know that we don't care. So it's a little odd. I'm going to just put a to-do in there. The downside of it, it's not a catastrophic failure because all it would mean is that you pick a slightly different position to sample your lighting from. But, you know, I don't know if that's... Again, if we haven't really done any kind of analysis to determine that we don't care, then we don't know if we don't care. So I am a little nervous about that, and I just want to put a to-do in there because I'm not sure we really thought that through all the way. It definitely will work. I mean, it's never going to give like a completely ridiculous result doing that. It will always give you roughly the correct hit, but in the case where you had 2 hits that were very close together, it will not correctly pick the closest one all the time. It will just be kind of random which one it picks. So sometimes it will pick the closest one and sometimes it will pick the one that's slightly further away. And I don't know to what extent that could have a significant effect on the quality of the lighting. In our particular case, maybe it just almost never would because you don't really care about those kind of fine-grained details in a game where you just have large sort of blocky, Minecraft-y looking sort of geometry that you're casting against. So it's possible that it doesn't matter, but I would at least like to note this so that we could maybe take a look at the lighting quality pass and see whether this is actually valid. So it's really difficult to say, and I think that's just a case where we should do some analysis on the actual numbers and see whether or not we have situations. You know, another one would be if we just wrote the laborious code here which tested exactly what the right answer was and then counted how many times we were wrong. I think that's something we should probably do just to make sure that we know exactly how inaccurate this is making us, right? That's really all I want to do there. And then if we're sure that it's fairly minimal, then it's probably still a great idea to do it this way anyway, because we want to minimize the cost. But it's just, since I don't think we really did that, I'm not sure I'm comfortable with it. Anyway, once we do that, if in fact that is okay, then we get back a min test value here by using the minpos EPU16, which will do the horizontal comparison of 16-bit values for us automatically. And that's the entire reason that we did this, was just because it's the one way we had that could actually do that comparison. We didn't have a way of saying compare 4 floating point values and give us the minimum, the index of the minimum. That wasn't a thing that was available, at least not that we could find. And so the reason that we had to do the 16-bit compare was because it's the only thing we actually have that will do a horizontal compare across the lanes. We then have this shuffle index, which is what we extract out of that. That's going to tell us that answer. We verify as we're running that it never gives us an answer that isn't less than 4. And the reason for that is just because we've padded this out in such a way as to make sure that we can't get, it has to be 0, 1, 2, or 3. These are just copies of the original 2 values, so you can't ever have one of those being less than this one. And we looked and it does go in order, so in the case where this is equal to this, it should still return us the lower one, which is 0. So we just asserted that that's true because we wanted to make sure. And then we go ahead and we look in the table and we grab out whatever the thing is that it told us it should be, and that we grab out the shuffle that puts that thing everywhere. So we then do our pshuff to make sure our t-ray just now has the correct value in all 4 positions, and then we go ahead and do our computations to figure out the normal. We take the sign bit of the ray direction, and the reason that we do that is because we know that the normal has to be pointing in the same direction as the ray, or I should say in the opposite direction of the ray, because we can't hit something that's a back face of one of our occluders. And then we go ahead and do our selection of X, Y, and Z. And this is why we changed what we're storing, is because we figured out that if we just use which t value got selected, the X one, the Y one, or the Z one, we can then know whether or not we're an X normal, a Y normal, or Z normal. So we can get the sign directly from the ray direction, and then we get the Y, X, Y, or Z, which one it is, just based on which of the t values we selected. And this was a very efficient way to create the normal compared to what we were doing before. It's just a few bit operations, and we get some accurate values out of it, we think. However, we haven't tested it. We could have slipped up in here. We could have a typo or a bug or something. And so we need to check that we're actually producing good normals with this process. When we actually finish producing the normals, we extract them here down to singles in order to actually use, because when we fall out of these loops, we're going to do radiance calculations that need to look up into a specific place in the grid, so things have to be dropped down to single. So we can just see. Is that to-do still relevant? Yeah, it's not. So we actually did the thing that this to-do was talking about. If you look here, we now only have 1 irradiance computation, not 2. So yeah. Anyway, what you can see here is, regardless of how you exit the loop, we fill out these values, and the reason for that is because these are the values that actually get used. You can see that in the case where we hit something, we produce, the normal and the sample direction and that sort of stuff. We drop them in here. And in the case where we just run out of time, then what we do is we step the ray forward to where we ran out, and we just say this is where you're going to probe. In the case where we hit nothing at all, so we just miss entirely and we were still under budget, at that point we just kind of say, like, hey, we don't really know, which is probably wrong. I mean, I would say that it might be the best idea, possibly to just exit on the cost metric dropout and say, we probably just want to do this operation when we run out of space as well. Hard to say. That's kind of a to be continued. I think when we do the lighting quality pass and we decide how we're actually going to be putting moonlight in here, I think we're going to probably want to say that if you leave the grid, I mean, ideally, we'd just do like if you leave the grid, I don't think anything happens. So yeah, I don't know. This is probably fine. So we then go and compute the voxel irradiance, and we use where we are sampling, which is what we determined up here, right? We pass that in, we take that fall off, and we actually do the fall off based on the normal that we're reflecting off of and whatever the emission would have been. We do some computations to get the RGB and emission to work properly, and then we pass those out. Right? So that's the complete raycaster, and we want to step through here and verify that those things are actually working the way we think they are, because like I said, there's a lot of intricacy in there. We've smacked a lot of things down to very few operations, or I should say very few. I'm sure we could get it lower than this, but it's still pretty small by compared to what the verbose version would be. And so we want to step through that now and see if it's actually working the way we think it is. Similarly, we also have the grid construction code, and that replaces the KD tree builder that we used to have. So in spatial partition for lighting, what you can see here is we had these things for building them. We're now running this separate path. We don't really care about any of this stuff anymore, and eventually we will remove it entirely. But what we're actually concerned with now is this part. What we do is we say, all right, let's take a look at what we need for our array, and we basically build the array on the fly. So we say, however big the lighting box is going to be, let's build that. We then loop through and we count how many leaves go into each square. So this is literally just a pre-pass for sizing so that we can keep everything aligned nicely where you don't have to jump around to figure out what you're intersecting with. You'll actually just always have, for every node in the grid, you'll actually know exactly what the leaves are in a tight array. Excuse me. I've been pretty sick lately. I got some antibiotics from the doctor because, of course, with COVID-19 situations, you actually can't safely go to a doctor, and a lot of doctors are actually shut down, so you can't actually get things like a throat culture or something. So they basically were like, well, let's try 2 treatment things and see what ends up happening, because that will be effectively a test, right? Which normally you wouldn't do. But in this particular case, if you don't want to have to go to the like 1 or 2 clinics that are open where tons of COVID-19 people actually already are, you don't really have a lot of choices. Yeah. Kind of annoying, kind of a really annoying aspect of the way we do medicine, where we don't trust people to do medicine. So like a throat culture isn't a thing that would be that hard for people to do at home. But of course we don't really, not only do we not trust people, but our society is set up so that people who screw things up because they're stupid or incompetent, like, will sue you and create like litigious problems for circumstances that make it so that you'd never really want to be in the business of doing healthcare at home. So even though really my problem could just be solved by me having someone like take a throat culture here and then mail that to a lab, of course that's not on the table. Yeah. Medical science, always 100 years behind. All right, so let's go ahead and, I guess it's not the science, it's the medical practice, always 100 years behind. So let's go ahead and take a look at how this is built. So you can see here that what we do is we grab the min and max node for the place that this thing needs to be inserted, and then we loop over the X, Y, and Z of the spatial grid nodes, and we basically say we're going to take this particular leaf and we're going to insert it into this particular AABB, so the occluder, and we're going to insert it into every node that it straddles. So, you know, all the nodes that it possibly touches, we're going to put it in there. So we're just counting. And when we're done counting, we then say, okay, we now know how many of these things we're going to have. So we loop through and we produce an actual total count by rounding up to 4 because we know we pack 4 at a time. And we produce the count here, and we produce the count undivided by 4. So it's actually just the raw count, right? So we say, here's where it would start, and here's where it would end. Oh, I shouldn't say that. Here's where it would start, and where it would end is set to 0. So it's basically like a start and a count. We then go through, and after creating room to store these, we do the exact same loop as we did before, but now we actually put each individual box in there. And we do that by creating what we think the box actually is, by creating the cell bounds for that particular location, and then we clip the AABB to those bounds using the intersect call. We put it into the leaf at the location that we believe it should go, thus creating basically a packed XXX, YYY, ZZZ for later use by inserting into subsequent entries in that order. When we're done with all of that, we also loop through and do a post pass to correct all of the information that we had here. So the first thing we do is we divide the start index by 4 because now we've packed everything in, so everything is by 4s. And you can see that we sort of did that here as well, right? The primary index was always divided by 4. We actually inserted it in. We then also come through here and we take the one pass last index and we also put that in using the divide by 4. And we round it up so to make sure that we capture the correct number in there. We then also say anybody who was actually erroneous, so they were an apron, they weren't actually supposed to contain anything. We actually go through and check for any of that. And if you are on the apron, then we put in the grid terminator bit or special value in the start index so that the routine knows, right? So that the grid, that's how the raycaster knows it's hit the end. So again, I think the logic is sound, but we don't know. We could have some bugs in there. There's a fair number of operations that have to occur, and we could have some part where we've got issues. This part here is a to-do that we now do, and so I'm going to turn this to-do into just a note. I'm going to say we need to use intersect here because we cannot allow boxes to extend outside their node region. Otherwise, early termination of the raycaster would not work since earlier T's could be worse, or farther, I should say, farther hits compared to later T's. So anyway, so that's just a walk through the entire thing. So let's go ahead and just start stepping through. I'm going to use debug build here. Excuse me. Because I'm not so concerned about speed at the moment. What I want to look at instead is just the behavior of the functions and to start looking for problems or issues that are not where something's behaving contrary to how I think that it should have. And so this is just for my own edification. Before I start debugging specific problems, I just want to take that walkthrough to see that we're not doing anything obviously stupid. What happened there? Is there a reason internal lighting core did not get hit? Oh, what's going on? Huh. Do I not call that anymore, or what's going on here? mean, here's internal lighting core, right? Oh, God. Wow. Not a great day for spelling, huh? Let's try that again. There we go. All right, so here we go into the actual lighting code that we care about. So this is the actual spatial partition build that we just said. This part is not something we actually work with, I don't think, but this part is. So let's take a look. Let's see what the max grid index is, just for our notification. So there's about 9,000 cells in the grid, including the apron. The nominal size is 6144. And then if you look at, like, you know, what happens, just to illustrate the +2, because on either side there'll be a little bit of the apron. You can see what we would get up to. That doesn't seem right, does it? So that's a little wonky. Let me take a look at what voxel dim is there. So if we did 26 times 18 times 18, yeah, it's doing the math right. So where is 8918 coming from? Voxel dim with apron. Oh, well, no. So I think that's a little confusing. Might just be a slow morning, but let's take a look at what's going on there, because I don't know. All right. So here's the equation that we're actually computing. We're taking the x and we're multiplying it by, well, I mean, if you compile this out, it's x times y times z plus x times y plus x, right? And I'm wondering if maybe so I guess the problem with that is this is computing the actual cell. Like, this is if you could actually get to the count as an actual index. So really, if you wanted to know the count, you'd have to subtract 1 from each one. So this trick, I mean, it sort of is still okay, because when you do this, you just want a value that's large enough, right? So it's not an issue, but it's also not really what you would want, right? So probably in order to make this be at least a little less confusing for anyone who was reading it, you know, we probably want to do this at least. You know what I mean? Oops. So let's just do that just to make sure that, you know, everyone understands what's going on, because it threw me for a loop there real quick, and it was like, you know, it's not a problem, but it's just like, you might as well be clear. So I think that's what you'd actually want, and in order to get the count, you would need to do +1. So this is the max grid index, but here we're actually doing a grid count, right? So I think you would want to do max grid count or grid count, something like that. And to be honest, I'm not sure why we just wouldn't do this with a get dim call. I guess we don't actually have one that does this, but you kind of just want like get total size to happen with this. It's let's just do this. I mean, that's just better, right? So I'm going to change this to grid count so that when we roll over these, we're a little bit clearer about what's going on. And, you know, I guess I don't necessarily know that we care what type that is, but we do want to never have larger than we can fit in 16-bit indices, because we don't really want to store large indices into these things. So now if I look at the grid count, hopefully I get an answer that's more congruent. There we go. So that seems better to me. Here's me allocating those. And then we're going to loop over all of the things we got to insert in. And so if we take a look at what we actually get back when we do these insertions, we should be able to see sort of how this works. So you can see here, like, it's basically getting, this is one that straddles, you know, as you would expect, most things will probably straddle it'll be a 2 by 2 by 2, right? I mean, that seems like mostly what will happen here, right? So as we multiply out the 2 by 2 by 2, you can see we just like adding it in there, right? And we're just putting these into the spatial grid nodes as they go. I don't think there's much to worry about in that particular computation. I mean, it seems like it should just be fine, right? But I guess what I would say, though, is this looks busted, right? So we need these things to be inserted, and that's just going to be garbage, right? I mean, if you look at what happens in here, this is expecting these to be inside the voxel. So things that are outside the voxel, cannot be inserted here, and we're not checking for that. How this wasn't absolutely destroying memory, I have no idea, but I guess it's just because we allocate things in a fairly consistent way. I mean, you know, right? Like, this should have just been a complete disaster. Let's make sure that doesn't happen by protecting ourselves from it. So I'm going to do an assert that the p-value is greater than 0 in each case. Greater than or equal to, I should say. And I'm also going to assert that it's less than the dim. So I think that's roughly what we want to do. Now, there's different ways that we could go about doing this. We could make this voxel larger. So, like, we can allow casting outside, and I don't know if we actually do want to do that, right? So if you look at what's going on in here when we do these get voxel index for p, we could choose to have the voxel be offset. So I'm going to put a to-do in here that says, do we want to support casting on a wider voxel area than the lighting? Because my hunch is we probably do, meaning the lighting bounds are fairly tight to the world, and we probably want to support lighting further out than that. In fact, I'm just going to go ahead and say, like, we do want that, right? So I think what we want to do here is we want to do some adjustment. I mean, you know, we probably still want something like this, but I think what we want to do here is say, look, we know that we have a specific region that's covered by the lighting voxels themselves, but we probably don't actually want to use that for the collision because we want to be able to capture things that are outside of that and still be able to cast so that we can capture lights that are off screen and stuff like that We don't want those things to disappear just because they're off screen, because the lighting will behave in an obviously erroneous way that we probably wouldn't like. So what I would say is voxel dim with apron probably is going to be something slightly different then. It's going to have to be larger. So if we look at voxel dim with apron, and the table, yeah, so if you look at where this is actually being used, right, we probably just want this thing to be larger. So you can see here that we enlarge it just with an apron, but the apron is not probably what we actually want. So we probably want to do another thing here, which is like the extra occlusion bounds, right? Probably extra occlusion radius. And what we would say here is like, look, maybe we want to go, you know, an extra 2 grid squares down, an extra like 8 grid squares to either side and up and down or something, you know? And so what we want to do here is say like, you know, let's make sure we build a much larger thing. And let's make sure that instead of using like the hot corner, which is what we would normally use, we'll use some other corner, right? So we have like occlusion corner or something like this. Or what is this called? It's called spatial grid corner. So we would want that where we could say, okay, the spatial grid corner is this thing that we're going to be able to look up in here. And what we want to do is we want to compute where that should be based on the apron. So when we compute the hot corner, which we've already done at this point, when we go to do the spatial grid corner in the solution, we want to go ahead and compute that by taking the hot corner, so this thing here, and I guess I'll make this called min corner as well, just so it's clear which one we're talking about. And what I want to do is I want to take the voxel cell dim, and I just want to step backwards by the occlusion radius, right? So we want to multiply whatever the vox cell dim is by that extra occlusion radius, and then we've aligned this voxel so that it's just like a larger version of the same, right? We probably need this value because without the extra occlusion radius and so on, we also wouldn't know. I guess technically the voxel dim with apron, I might roll that in there too, because at this point, since now they're basically separate voxels, we probably just want to say, look, here's the radius, and that's going to be the same value as the offset, right? So in here, we could store this as that radius. So I could say like, okay, you know, this is what the offset actually is. And that way, when people are doing computations on it, they'll use that and they'll be correct. So I think most everything else stays the same. We just have to change how we're doing that indexing. So that will be a little bit different now than it would have been before. So now when we come through here and we do this spatial grid nose grid index from, like this bit here, the problem we're going to have is get voxel index for P is not determinative anymore. So there's a couple of different ways we could choose to do this, and it's unclear like exactly which way we want to do it. But what you can see here is this will adjust to the min hot corner, but we now know that there's like a different corner that we might want to use sometimes. And so possibly what we should say here is instead of you loading that stuff up out of there, maybe we pass the min corner in, I don't know. And we say something like, okay, send us the min corner and then the p. And so here we would say, look at the min corner, and off we go. Now we don't need to actually do this. We can just get the p directly. Oops, that's not what I meant. I just meant that. Right? So in theory now we should be able to just do get voxel index for p, and we can pass the min corner that we actually want, which is the spatial grid min corner. And, you know, it occurs to me that we probably should have a data structure that's like voxel, that has like these things in it, and then you just pass which one you actually wanted. So we may want to make a utility for that at some point. I just don't know that now is that point. But like, you know. We'll look at that a little bit later. So now we come through here and we step through this. We'll now get grid indices that should always be in line if they're inside. The problem is we do know that we can have geometry that could be outside. And so what we really want to do is just say, look, this stuff should be clipped or clamped to the minimum and maximum places that this thing can actually be. And so I think what we want to do first before we do this is to take like the box itself and clip it to the entire voxel. And if it's outside, it will get clipped in. If it's literally like completely outside, we'll end up with a box that doesn't have any volume. And so we can just kind of discount it, right? There's other ways we could choose to handle that, and I don't necessarily know that any of them are good. So I think we probably just want to do that, but it's worth noting. So for example, if we wanted to, we could just say, hey, anyone who is outside just gets thrown into the apron, because we know that we're about to romp over the apron with a Terminator start index anyway, so that would be fine. But it just doesn't make sense to spend a lot of time on geometry that's outside what we're looking for anyway. So I don't think I'm going to do that. But it's worth noting that you could, right? So what I'd like to do now is I'd like to just go and create a rectangle 3 for the actual voxel. And, you know, I'm just going to do it. Let's just make an actual function in here. I mean, an actual thing. You know, we've got the atlas, the handmade light atlas, right? Let's just make like a handmade like voxel, right? And if we wanted to do this, we kind of already know what they would take, right? I mean, this is what we want in there. And so if we have a voxel grid, or a voxel dimension, I guess you might say, voxel spec, I don't know, what do we call it in the atlas case? We just called it light atlas. So let's just say it's a voxel. I mean, voxel is, it's not the right term, because voxel is a pixel, so I guess this is a voxel grid. I don't know a way to say it. So in here we could just say, look, there's a rectangle 3, that's the total bounds of the voxel. And then there's the actual dimension and the inverse dimension. And I think that's all we need to produce like the correct calls that give us all the information we want to know, you know, out of this. I mean, I think that's just everything we need, right? So then if we like take a look at all the things we're actually trying to do here with these voxels, so, you know, we've got this sort of stuff. All of this is stuff that now we should be able to just put in here and compute. So all of the previous, you know, voxel-y sorts of things that we were doing, we should be able to have them all work off of one of those structs. And that's better because then we're just not sort of spamming those calculations everywhere and possibly getting them wrong, you know, which is not what we want. So I'm going to pull all of these out and I'm just going to take a quick look through the code at that point to sort of clean it up and make it all call through here directly. And this probably will break our ability to load our lighting stuff, so we're going to have to probably take a new lighting sample, but that's okay because that's kind of been a long time coming anyway. So let's see. I don't see anything else particularly suspicious in there. So, you know, assuming that this is what we think we might want to do here, I'm just going to like sketch these out. So we think we have one that wants to take the center for a particular index. And in all of these cases, we probably want two versions of this, like an absolute index and a regular index. So we'd probably have something that does like these two different versions, you know? And I mean, I guess another way to do that would just be to say, I'm going to hold off on that because it is harder to do. So I'm not going to produce ones that we don't actually know if we need, right? So yeah, let's not do that quite yet. So each of these works on the blown out coordinates like X, Y, and Z. And then this can be a world P. And then just this one produces the flat index, right? So get cell center P, get cell bounds, get index for P, flat index from, and then maybe like a utility function to get the total bounds. I think they can just go ahead and reach in there and get it because I'm not going to want to change that storage. So I think we're fine. So let's go ahead and put these in place. So get cell center P here. All we really need to do is say, all right, we've got the total bounds, dot min, and then the grid voxel dim times the index and the centroid offset. Get voxel cell bounds is now just plain get cell bounds because we know, since we're passing grid as the first parameter, that we know exactly what we are asking for there. So get cell bounds just says, look, produce the cell bounds by taking the grid total bounds min and adding these two. Now, I don't know why we wrote it this way. That doesn't really make any sense because after you've computed this, why wouldn't you just add it in? That was a really convoluted way to do that and doesn't really make any sense, so we're just not going to do that anymore. So this gets the cell bounds for us here, and then we've got the get index for P. This one is the reverse mapping, so this one is trying to figure out based on the world P that you give it. So in order to do that, we need, again, that minimum corner, total bounds min, and we're using the inverse dimension here. And then again, we subtract out that center value. Which I thought we fixed this. I guess we didn't fix it because we were doing it in 2 different places. So kind of another reason why this is, something you probably want to do a little bit more centralized. But if you take a look here, right, this is wrong because when you do the floor, it's not rounding, it's flooring. So to create the correct center value, it should be that, right? So we must have had some other bug in there. That's why we put in that correction and we just didn't think it through or something, because that shouldn't be the case. Once you subtract the min, then until you actually go up above the cell dim number, until you go above 1, you're in that cell. So the correct cell index in this case is this, and it may have been because we were doing something else with it at that time, but the actual index for the cell is always this. So I think that was just, again, just a screw up on our part. So we now have the grid index from. This is, again, something that just needs to compute. It needs to be in bounds. We can also produce a thing that tells us that value. So we can say like is in bounds, and we can use this as the actual check. And then here we can just say assert that it's in the bounds. So we would just say for this voxel grid and this p-value, this is actually an index value, not a p-value. So for that particular p-value, off you go. Oh, you know what else we need here? Is the count. So we need the cell count, right? So these are the dimensions of the thing, but we didn't actually store how many cells there were. We do need to do that. So in here, this is actually cell count x, cell count y. And when we do in bounds, we're going to be checking the cell count. So I'm going to pull the cell count out here just for ease of my own referencing. So just grab that value like so. And we can now test if things are in bound by testing the index. And instead of asserting these, I'll just pull them into a function. So the result of this function is just going to be the anding of all of these. So if all of these things are true, so if all of these things are true, then you get the result of it being inbound. If any one of them fails, it means that one of the indices is out of range, at which point it will return false and fail. So we can assert that it's inbounds here, and people can also do the check for inbounds later. We now produce the flat index. This is supposed to be flat index rem. And I think that's what we want. So now what we want to do too is say, okay, we need a way to create one of these. So this is make voxel grid. It's going to return one of these. And what we're going to do is initialize the values in it to various things. And we're going to make it as easy as possible for people to construct by computing all of these values based off of just a few basic values that they pass in. So in terms of these actual values, all we really need is the cell dim. So if you pass in the cell dim and then the count, right? So we have this many of this thing or something like that. Then from there, we can initialize the cell count and the cell dim directly. Also, I don't know why I didn't just call that cell dim. Let's fix that. the other values can be computed from that. So, you know, the inverse cell dim is just 1 over the cell dim, right? And the total bounds is just going to be the cell count times the cell dim, right? So this is a Hadamard product. Now we do need one more piece of information, because with only this piece of information, we wouldn't actually know where it is. So we need to know what the minimum corner is, and we can add that in here. So here they just pass what one corner, how many cells there are in it, and what the dimension of each cell is, and then we'll fill in all the dependent values based on that, right? So like the max and the inverse, which are computed off of it, they don't have to pass those in, because we can tell what those are. So that will make a voxel grid for us, and this will presumably allow us to, you know, write some utility functions as well that are, you know, if we have two different voxels and we want to translate between indices and from one to the other, or things like that, presumably we should be able to do that as well. We'll see. So let's take a look at now what happens in the lighting. If we were going to do this and move from here, what I want to do now is take a look at how we would actually place this in the lighting. So let's go ahead and destroy our ability to run the current sample code, because, I mean, let's face it, it's not going to happen. The box ref count and the boxes, all this stuff is gone. So I'm going to go ahead and say, look, we're going to end up with just this now. I would also say that, like, the scratch ABC nonsense, we can pull that out of here too, because even if we want to run the spatial partition stuff, that is still using that information, so you can see it like using the scratch stuff. What we can do instead is just now push those on here as array pushes, because they don't need to persist outside, right? So when we go through here and we need like scratch A and scratch C and all this garbage, we should be able to make that work without ever actually having those, you know, having to keep those inside the lighting solution. So we can have, you know, and in fact I could just do them like this, but I probably don't actually want to because of the size of those. I don't know if there's any downside to me just doing a push. I don't think anyone does an array count on those, do they? They don't. So I should be able to just literally do this, where we just do a push array here, and each one of these, oops, just creates the same table that we used to have, but now it's actually, you know, actually, if it was me, which it was, I probably would have put the type second. So we can just use the temp arena now that we pass that through properly for all of our scratch space, because we know that doesn't need to persist frame to frame. So that's just, you know, a handy little thing. It looks like we accidentally deleted something here, though. Yeah, we did. There we go. So now we can start to collapse this down a little bit. So the scratch buffers go away. Eventually, like, a lot of this stuff will go away. So the box count in the boxes and the root box and all that stuff. This will all go away as well. None of this stuff is necessary, I don't think, because the boxes can just be passed through directly. So I think a lot of that stuff will just get removed. Okay, so looking through what we actually have here, again, the Voxmin, corner, Selden, this stuff here. So we now have two of these, right? We have the Atlas grid, which is how we're actually storing the lighting information. And then we have the occluder grid, or the spatial grid, I guess. And I don't know that those are the best names, so we might want to think about this a little bit. Like, there's the lighting atlas, and that has a grid associated with it. And then there's the, like, actual spatial queries. And so I don't know if atlas and spatial might be the best, or they might not be. So we'll see. And I think that's probably all we need. So if you look at like these things here, we probably still need that one because it's a non-obvious thing that's a little bit difficult to derive. You wouldn't necessarily know that these things are exactly offset just by looking at them, and you'd have to do a floating point comparison to determine that. So you probably don't want that to happen. We don't need this. We do need the light sampling walk table. And the rest of this stuff looks like pretty harmless, right? The diffuse weight map is probably something we want to generate offline as well. But, you know. I would say nothing else here looks particularly suspicious. So I think this is okay now. All of that looks fine. And so when I'm actually initializing this stuff now, I'm going to have to change where I'm actually asking for it, right? And so I'm going to go into Handmade. Well, I guess at the moment it'd be HH Lightprof, and I'm going to include that voxel. And we also need the CPP for it, so we'll include both of those. And now we need to just debug anything here that is incorrect. I'm not sure what the problem is. Oh, so the flat index from, in this case, we've got the safe truncate to U16. I mean, I guess we'll let the person on the outside do that because, I mean, hey, if someone does want to use this in some place where they've got like a really large voxel or something, there's really no reason we have to do that here because everything else in the system supports it. So it seems pretty straightforward to just return it this way and call it a day. So I'm totally fine with that. The person on the outside can verify the value. So in this case, cell count, we didn't actually pull it out. We should have. In here, we've got the cell count and the cell dim Hadamard product. This needs to be lofted up to a float in order to do that multiply. So that's got to happen there. And this total bounds here, I didn't quite specify it properly, but so what we really want to do here is say that this is a rectangle min dim. So, you know, here's the minimum corner, and then here's the dimension of it. And that will create it for us, I believe. So at that point now, all the things that we were calling before, so all of this stuff, all wants to be calling our new system now. So we pretty much just really, you know, honestly, we just want to vaporize this whole thing. And then we've got to think about what we want to do for this. And so the reason that this is a little bit tricky is because it actually needs the F chord to produce the remainder. And so I think what we probably want to do here is actually have a composite return that gives this information back because you know that this is something that you're going to want. So like the UVW coordinates, for example, are things that you often want to use there. And so although this B chord is something that is unique to what's going on here, this is actually a computation that's probably what you would want to do anyway. So I'm going to call that something along the lines of like I'm going to call that something like voxel relative P. And it will just have this information in it. So inside here, what we'll do is we'll say, all right, so there's an index that we're going to return to you. And then there's a UVW. And the B chord in this case doesn't get used outside, so we probably just won't return that for now. If someone actually ends up needing it, then we'll start passing it. So then in here where you actually call functions like getIndex for p, those will actually go through a separate thing that's like getVoxel relative p. So when you call this function, to get the relative p-value, it's actually going to do this instead. In this case, we know we're always filling out the entire result, so it's probably fine to not initialize. So here we're going to say, look, the result UVW and the result index are computed here. Oops. And we know the inVoxel dim, and we know the total bounds min. And the world p goes here. So that's our entire thing. And now for getIndex for p, what it can do is just say, well, you know, the result is just get relative p of this thing and just only take the index. So it's just a utility function at that point, which we don't really even need to provide if we don't want to. But for now, we just will keep it so people who were calling that can still call it. All right, so now this function can just do voxel relative p to get out the like a rel p value or a vox rel p, get relative p. And it'll pass the atlas grid, which is what it's using, and the sample p, which is what it's sampling. It'll then have the values it actually needs, and we probably want to leave those so we don't have to rewrite the rest of this function because they're just different names for the same thing. So what we can do here is say, well, what we needed was a voxel index and a UVW. We have both of those two things, and here they are. And the rest of the function should be able to remain, in theory, unchanged. All right. So that's all fine and good. Later on in here, what we need to do now is figure out how we're actually going to get the rest of these values that we need. So in this particular case, where we have voxel dim with apron, that's not going to exist anymore in anything that we actually need to look at. What we're going to do instead here is probably just offset the grid index value directly. So probably what we do is we'd say, okay, the grid index that we're going to have, what was it called? Flat index. We're going to ask for the flat index, and we're going to ask for that in the spatial grid. And what we're going to ask for is specifically the voxel index that we're at in the voxel dim we're actually using for our atlas, right? For our spec atlas. And we're just going to go ahead and take that and offset it by the offset value we stored here, right? So I guess what we'd call this is like atlas to spatial grid index offset. So we're going from the atlas to the spatial grid, right? So that would give us what we expect. This is going to have to be a safe truncate because, again, the voxel routines don't necessarily... What is happening there? What the heck? I do not know what is wrong here. Okay. So I believe we've got rid of the bugs, but I don't know, ForCoder is very unhappy about that. So let's do it this way. So this way the initial grid index is computed and stored as the 32-bit value. And then what I'll do is when I was going to go use it, which is here, I'll do a safe truncate there. So that way we just know, like, hey, we'll downshift to 16, and if somehow we blow out that address space, it'll assert and we'll know. So then when we want to do the box center P here, you can see us doing like a computation to get that. This is not necessary anymore. So Vox center P presumably isn't a thing. Yeah. So all we need to do here is like get cell center P and pass the atlas grid and so yeah, like interestingly enough, let's look at this for a second. So you can see here we were constructing this index and we needed this index up here. So I think what we want to do is like just say like Vox index. And I think we just want to have this, right? Because it looks like we need it in a bunch of places. So here's our Vox index. And we can call this our Atlas index maybe. So that way when we do this, we can, you know, just say get cell center P solution Atlas or Atlas grid, and then use the Atlas index, right? And that gets rid of all this code. Now, what you might notice is that like the spec Atlas itself also has the dimension in it. So it feels like maybe those things kind of want to be regularized a little bit, but unfortunately I don't think you really want to do that because they're sort of a little bit separate. It only cares what the dimension of the voxel is in the actual atlases. They don't care about min corners. So it'd be a little bit weird for them to have their entire voxel in there, and you just have to update them all the time, which I don't know that we really want. Now, maybe we would say, well, okay, what if we maybe wanted to store them aligned separately? I mean, I don't know that that would even work because they need to be transferred between, but so it's hard to say. Like maybe you unify those eventually, maybe you don't. Certainly haven't seen enough quite yet to know, so I'm not going to do that just yet, but looks like this is a U32 for some reason, and I don't know why, because the rest of these aren't. So let's keep going. Okay, that doesn't need the second close quote anymore. So in here we've got the spatial partition build for the KD tree in here, and we're building both of those. I don't really want this anymore. I'm pretty sure we're just never going to use these again. So I'm not going to port the KD tree build at all. I think it was a thing we went down that just didn't pan out and isn't actually as good as the grid version. Okay, so in the box index stuff here where we're doing the get voxel index for P, these again are just going to be get index for P's, and they're going to be passing, in this case, the one that we actually want. So it's going to be solution spatial grid. And now that's a lot cleaner. Like we can see what's going on there and it's not weird, right? I'm not sure what it doesn't like about that though. Why is it complaining about that? Oh, it's not. It was just kind of old news. All right. All right, so now what we need is we need to do the flat index from here, where we say that we want the flat index in the spatial grid, you know, from this index that we actually have. I'm going to make that be a box index here, right, or a spatial index, just so it's clear what's going on there. And what I'd like to do here is I would like to add the code that we had been working on when I went down this road of cleaning up the voxels. What I'd like to do here is just make it so that these things are properly clamped, right? So, you know, I'd like to do something along the lines of rectangle 3 clipped box equals, you know, box min, box max, rect min max. So if we build a spatial rectangle here and then I intersect this with the solution spatial grid total bounds, now I will have clipped the box so that now we get, you know, a box that's guaranteed to be inside our voxel. And I can also just do here, like, hey, if this vox is actually didn't get entirely removed by that clipping operation, then we'll insert it. And that to me seems like way better. I thought we had that. Guess we just still call it has area. So I think that's all good. Let's try that again. I'm not sure why it does that double. I think that's maybe because it's a later compilation. So I think the problem we're having there is like we haven't actually included this in here, right, in the Handmade build, so it doesn't know what a grid is when we get there. So let me just, even though we're not working on the Handmade Hero actual main body of code here, let's just put that in there. Okay. So the get voxel index for P, where we pulled that out before, we want to do the same thing again. So it's a little annoying that we do this code twice, but I'm not really sure how else we would do it because we do need to do that counting procedure. We've already produced the box bounds here, so another thing we might do is just say, well, let's make this unified so that it looks the same, right? So now what we want to do is we want to do the clipped box version, and you know, we could just make this here be box bounds. In fact, maybe that's how we'll do it. So we'll just actually say, look, box bounds is this clipped version. So then in here where we did box bounds before, we're not going to do it that way. We're going to do clipped bounds, and then we're going to check for the has area, right? And we can also do this and this. And then we just need to close off that check. So now I think it's okay. So we've got the box index. We check the clipped box, make sure it's in there. We go through the loop to figure out where we might actually hit. Oops, this is box bounds now. And then assuming that it actually can hit somewhere, we'll actually go through and insert it in, right? Okay. Now, there may be some issues with efficiency in that code because we're not telling it about pointer aliasing or anything like that, but I don't really care about the performance of this code at the moment because this code probably isn't really implicated much in the performance just yet. If we actually see that it starts to be implicated in the performance, which it might, then we would look at maybe streamlining this because it's not very well written at this point for speed. It's just kind of doing what it needs to do, and that's the end of it. All right, so now as you can see, we're kind of going through doing this spatial index one last time to clean some things up. So we want to do sort of the same thing we were doing up there down here rather than doing it this way. Otherwise, there isn't much else to say. When we do our lighting initialization now, we actually want to do initialization of these values properly. So we want to be able to take like the Voxel dim and the inVoxel dim and that stuff and set that properly. Now, to be honest, at this point, I don't really think that we probably need the init lighting code almost at all. Really all we probably need there is the random seed, because the Voxel dim and the inVoxel dim are things that we can just get every time we run through. So honestly, it's unclear how much the init lighting call really needs to happen. Yeah, it just doesn't, it doesn't make a lot of sense. So I think what we probably would do here is we'd probably pull this stuff out and we'd probably go ahead and roll this into the lighting computation stuff. The solution works here even. I don't even know that that needs to be there. So I think this comment is also correct. So if we go down and look at where we're actually doing the dispatch, I don't know why we would not just do it here using the temp arena. Before we didn't have a temp arena, we just hadn't thought about that and we hadn't really done that. But it seems pretty clear at this point that that's what you would do, right? So like, for example, in here, if we were to just say, look, there's just a work array. And we know how many there should be because we computed it. We'll just push that on right here, right? That's like way, way better. It doesn't pollute the structure with garbage that doesn't need to stick around, because those values are only valid when you're actually doing lighting work anyway. There's literally no reason for them to ever actually be there in any other circumstance. So that totally gets us out of the business of bothering with that garbage, which I think is way, way better. So I think that's good. And so again, I think a lot of this stuff can just go away. The light sampling walk table is not something that can go away. That's something that has to get computed probably only once because it's expensive to build and we don't probably want to build it every frame. So taking a look at init lighting now, I think I'm going to go ahead and move this stuff all out of here. So I don't know why update debug lines is set to true. I guess just because in general we update those. We just don't put any on there if we're not actually using it. But we're going to leave that as it is. And I'm just going to say, all right, this stuff is going to happen in here, right? Oh, well, I guess, you know what? The fundamental unit, though, getting passed down. I mean, really, yeah, again, that can just be something passed. You know, it really could just be passed every time. It doesn't need to be in init lighting, right? Like the lighting doesn't really care what the fundamental unit is. It can change the voxel dimensions if it needs to. I don't think that really matters. Yeah, so I don't know. That's a good question, and I'm not sure what should happen there. I guess I'll... I mean, I guess I'll just leave it in there. Let me go ahead and see where that's actually called. So here's where the world mode fundamental unit thing comes in, and you can see it, making this call here. And so, if the world mode fundamental unit is just sitting there, then, we could just pass it to begin lighting. I mean, there's no reason not to. So when we do begin lighting computation, we could just say like, hey, yeah, like, here's the fundamental unit, and you can have that. So there's really no need for this routine at all. And I guess mostly, the only thing it's really using here is the random seed. So that entropy unit, needs to be set somewhere. But again, I don't think that's something that really would warrant actually calling this. So, maybe we just do something like this. So oops, that's no good. So the random series here, where we do the random seed out, I would think that we could just do some kind of an initialization check here. Like, I mean, we could just do a thing where we said like, if we were gonna initialize the Voxel dim, then we initialize that stuff too, right? Because it's just like, it's dumb to have an init call that you have to make for no reason. Like, why bother making the people who use this call init when we don't really need to? We can just check some parameters, and when we think that we have to update, we just update everything, right? So let's do it that way. And let's say like, okay, so when we come through here and we want to know about the fundamental units, and maybe what we do is we just say like, what's the fundamental unit? And we say, if the solution fundamental unit is not equal to the fundamental unit, then we now make it that way, and we update all of our base information, right? We could also make this be sort of like a giant like recompute kind of thing. So what we could say is like, all right, so if you change any of the parameters of the lighting system that are fundamental, so if the fundamental unit isn't the same, or you change the dimensions of the voxel, so now we're computing like higher resolution lighting or something, then we just do, all of this stuff over again. And I like that a lot better, because now we can just say, look, there's one init place that even if, if you're running and you want to like eventually support things like changing the lighting resolution on the fly, this way we know that all of the reinit stuff can just be done in one place, and we don't have to worry about exactly what the heck is happening there, right? I think that's way better. That just seems a lot nicer to me. So then we can say that we've got our table memory and our temp memory. Those are basically sort of split there. And then we can just focus on the rest of the stuff and make sure that works all right. I'm going to demote all this old stuff down to the bottom, because it's going to go away, so that we can just focus on the things that we actually have. I don't actually know that debug light p is really going to be used much at this point either, so that'll probably go away eventually. But the rest of the stuff here is stuff that we actually believe we will probably be using at some point. The debug lines obviously maybe will be a separate thing, but we'll deal with those a little bit later. So the rest of this stuff is stuff that we would expect to actually preserve. And so let's try and put these where they belong. So the light sampling walk table, and like the grids, like all this stuff is stuff that we expect, same with the series, I guess, in a sense. All all of this stuff is stuff that we expect to sort of have persistent and that's initialized when we start up. All the rest of this stuff, so like from here down, is stuff that we don't. And I guess the diffuse weight map would also be a thing that would be that way. And the sampling spheres and that stuff. So any of this stuff would also be initialized only once. The rest of this stuff is stuff that's kind of in flux. So this is all stuff that can just vary or that's done temporarily. The spatial grid nodes and the leaves, these are values that don't persist over time. But we don't really necessarily want to have to pass those around everywhere. So in other words, normally what we would do is we'd pass these down. And at the moment, we're not doing that primarily because it just seems like an inefficiency to constantly be passing them everywhere. But what we could do is say to do, wrap these in their own things so we don't leave them in the lighting solution since they're allocated in the temp arena anyway. So that's kind of a separate issue that we probably want to look at some point, one way or the other. All right, so it looks like we're just about out of time. I'm going to go ahead and just finish up a few more of the compiler parts here, and then we'll go from there. So the table voxel dim is now really has to be the same as the spatial grid. So what we want to do here is say, look, if the voxel dim for the spec light atlas, we're going to have to produce what we would expect the spatial grid to be. And I thought we had that in here somewhere. We were doing the apron offset, but I don't know where that went. Or atlas to spatial. Here. So here in the internal lighting core, like this is that stuff, right? And we have the voxel dim with apron. So this stuff doesn't want to be done this way probably now, right? So what we want to do is we want to move this stuff out into the begin lighting because everyone wants to see it. And then we want that voxel dim with apron part to go away. So if I go back to begin lighting computation, then in here where we've got this stuff happening, we want these computations to happen up front so that we can then compare them and see whether they're correct. So in build spatial partition for lighting, the voxel dim with apron should not actually be happening anymore. And so in begin lighting, in build, here it is. In build spatial partition, voxel dim with apron should just be something you now get out of the solution because it's like a known value, right? So in here, when we're talking about voxel dim with apron everywhere, that's just not necessary anymore. When you look at the grid count here, this could also be something that we just call and get the voxel. So we could just say like get total cell count. And in here, we wouldn't be using voxel grid with apron. We'd just pass the spatial grid. And so then in our voxel code now, we can just say, hey, get total cell count. And this will just tell us the answer to that question directly. And again, this is very simple. It's just the cell count x times the cell count y times cell count z. Right? No big deal. So at that point, the apron should not really be used in here, I don't think. Yeah. So now the only thing we need to adjust is when we're actually looping over these. This needs to loop over the one from the actual spatial grid. So this is like solution spatial grid. And in here, we have to do the cell count z, right? And it's worth noting that there's like other ways that we could actually do this. So we don't need to actually write the loops this way if we don't want to. We could instead write the loops over the spatial index by just declaring a thing that increments a spatial index by incrementing the x, and if it rolls the x, increment the y instead, and so on. And it's hard to say, like, one of the things that C makes very difficult is injection of that kind cleanly. It's kind of a long story. It's not worth going into right now, but languages in general do a bad job of loop insertion. And, you know, so I'm probably just going to leave it the way it is at the moment and just chalk it up to kind of one of those unfortunate aspects of things. Okay, so moving along, this again is just the spatial grid cell count. And you know what I could do here is I could just pull cell count, just so this is a little easier to read. Okay, so now we just are left with the init code, and we have to get the init code right. So what we want to do here is say, well, all right, the spatial grid index offset. Also, by the way, like now there's should be no calls to init lighting. So, you know, in init lighting, that just doesn't have to occur anymore. And that's nice too. All right, so in here where we're, excuse me, in here where we're doing our pre-computation, we just want to make sure that all of that works properly. And you can see that there's a lot of places here where we're doing operations that were previously looking directly out of the, that we're pulling values directly out of the lighting that now should just be based off of the voxel. So the spatial grid index offset now is not called that, but it is still a thing we want to keep. It's this, right? Atlas to spatial grid index offset. And so then what we want to do is we want to generate our two grids. So here we've got an Atlas grid and a spatial grid, and we want those two to both be initialized. Now the tricky part here is that we want to make sure that we detect changes to the grid. So in situations where we're getting a different voxel dim than we had last time, we want to be able to detect that. And we should be able to do that fairly straightforward by just saying, look, if the Atlas dim from last time is different than the, you know, one that we used last, then if the thing we would be using for the Atlas dim is different now, like if it changed, then we need to trigger a readjustment of everything just like we were doing before. Otherwise, we're fine. So we do need to know the Atlas spatial grid offset, and we need to set that, but we don't need to set that unless we're actually updating things, right? So in here we can set this, and set these, and let's just go ahead and make those work. So we need to initialize these two grids. So we want to do that at some point here. You can see us computing a lot of the dependent values. So we want to do our Atlas grid. That's the easiest one because it's in line with what the lights actually are. And then we have the spatial grid, which is like the larger one. Now, if we look at what goes into calling make voxel grid, we've got the min corner, the cell count, and the cell dim. So for each of those, we have to be able to figure out what that actually is. Now, the min hot corner is actually something that gets adjusted like as we go too, so it moves around, right? And you can see here like how we're actually creating that value. You can actually see it getting computed here by using like the origin positions and such, right? So we still want this code to actually execute. And so what we're kind of going to do here is probably just make it up as we go. Because any time that the solution itself changes like this, we kind of just want to clear everything and restart the lighting because we know that like we can't really use any results that we had from before because they're not going to be valid anymore anyway. So it probably should be fine. So I'm guessing what we want to do here is we want to set the Atlas grid and the spatial grid. But probably since the spatial grid is always dependent, we can probably do that after we determine where the atlas grid actually goes, right? And I think for purposes of computing the walk table, we should still use the old atlas grid dimensions. And the reason that I think that is because I don't want anything to cast all the way across the larger grid. I want the maximum size that you're ever going to walk. Well, so that is a bit tough. These walk tables are just going to be huge is the problem, and I don't love that. So I guess for now, all right, so here's what I think what we probably want to do. So looking back at the grid raycaster, right? So the cost metric, when we run through here, we deck the cost metric once each time. So like the maximum cost metric here is bounded. So I think actually this we could get rid of. When we go to compute walk table, what we can do instead is just have the maximum cells visited as a thing. So instead of ever checking that value, like instead of this, what we can do is just say, did we ever go that far? Right? So that seems way better because if we have that cost metric in there, then I think we, because before we were thinking that we wouldn't have to check the cost metric, and now we kind of do. So I think we'll be okay. Yeah. So I think what we want to do instead here is actually say what that's going to be. So I'm going to say solution like max cost metric here, and I'm going to set that to something. And, you know, at the moment when we did our grid raycast, you know, what did we set it to? It was like 16 or something. Yeah, so the cost metric here. So I'm going to say like max cost, you know, per ray, that sort of thing. And we'll say, okay, the max cost per ray is going to be 16. And then we just need to tell the walk table that that's what's going on. So it's going to get that max cost per ray, and it's going to go from there. So that'll be good because then we have unified those two code paths and we know what they should be. So max cost per ray goes here. All right. So I do want to take a look at the compute walk table code. I also don't really know what it's doing that for. So that's kind of stupid. So this is dumb. And so probably what we would rather do here, right, is do this. So that way, you know, we're just computing the table and then returning the table, right? So that way this doesn't ever take the solution, and it doesn't even know what a solution is. It just takes some information and goes from there. And then I can also return that dest, because I don't think dest gets updated, right? So it should be okay. So I think that's all fine. And now we can compute that table, and that'll work with the cost per ray. So then what we'll do is we'll say, all right, instead of the Voxel dim, I'm sorry, instead of the Voxel count, we'll just say what's the max cost per ray. And when we loop through these and we try to determine when we should stop, what we'll do here is instead of tracking span, which I don't know that we ever actually need to track, just take a look. Yeah. So span is only ever used for that count. Instead of that, all we're going to do is say, look, if the cost at this point has exceeded the max cost per array, then we stop. So in here, each time as we go, we'll say like if the cost is greater than the max cost per array, then we stop. All right, so that feels way better, and it gets that dependency out of the mix, which I think is good. The max desk count now, we know it's just the max cost per array, so we now could just say, look, it's however much that max cost is, because that's what we're stepping up to. So if we ever exceed that cost, then we're done. I guess I should say if it's equal, right? So if we're, I guess another way to say this would be, actually this is just a while loop. So this is, while cost is less than max cost per array. Keep going. And we may want to pad that, I don't know. So, so like padded max cost per array or something. So we may want to let the tables go a little bit further. I don't know if we want them to be exactly that tight. So let's just do it like that. Wasn't quite done there. There we go. Okay. So yeah. Oh no. Yeah. All right. So I take it back. Because we use the step, we flatten the step down to just be a direct offset. There's not going to be any way around it. Yeah, so that is going to have to be dependent on that voxel dimension, right? Because if we want to bake the offset in directly, there's no other way to do it. Yeah. So that's unfortunate, but yeah, that does look like what we would have to do there. So I guess voxel dim does have to be there, right? And so when we actually pass this in, we're going to have to be able to, we're going to have to know what the total cell count is, right? And that's pretty much all there is to it. It's not the end of the world, but yeah, it'd be nice if those two things were independent, but I don't think they're going to be. All right, so we know what the voxel cell dim is. So we know that whenever we set the fundamental unit, we can then make our voxels. So our atlas grid, the vox cell dim and the invox cell dim is, at the moment anyway, going to be the same for both of these. So the voxel dim can be passed to both of these functions, and it's always going to be the same. We don't have to do anything weird there. The voxel dim, on the other hand, or the cell count, as it might be called, is going to change. So basically, like the difference here is going to be this voxel dim with apron. So, these two are different there. So I'm going to call this the cell count instead of voxel dim. And I'm just going to say the spatial cell count and the atlas cell count, right, are going to be different values. So in the case where we have to recreate these, we know what the cell dim is because it's always the same, and that'll never change just based on the fundamental unit. When we come through here and we set the Atlas spatial grid offset, that is actually something that's always the same. So we don't really need to initialize it here, although we might as well, because why do it more than once? When we get the spatial grid count, we know what that actually is. It's going to be the Atlas cell count plus that spatial grid index offset, so it's plus this value here, and we want that on both sides because it's a radius expansion basically. And then when we compute the corners are actually going to be specified sort of down here, right? So when we compute the corners, that's probably going to happen in a different place, which also suggests to the suggestible listener that make voxel probably is not exactly what we want, right? And again, write the usage code first. This just happened to be something that I threw in there. It doesn't really seem to be right. So if you take a look at how it actually works, we want to be able to rebase that fairly frequently. So probably what will actually happen is this. And the total bounds will actually be recomputed fairly often. So the min corner will come in here and it won't come in there. That seems a lot more like it. And again, that's just based on looking at how the usage code was working, and we want our API to like play well with that usage code. So this is actually what it should have been, and now we know. So make voxel will only take the cell count in the cell dim, and hey, guess what? That's exactly what we happen to have. And now these two things have converged nicely. So I think that's good. The rest of this I'm going to ignore real temporarily here. So the voxel dim here, we can actually loft this value. Like this is always going to be the same, so it's totally fine if these all want to use the voxel dim like this. Although since they're using the inv as well, like I'll just have it get them out of here. So in this case, we're going to talk about the Atlas grid cell dim, and the inv voxel dim is the Atlas grid im cell dim. And again, these are probably things that we will want to play with a little bit more later, but I'm just going to leave them for now since I don't really want to get into this part of the code at the moment. But all this is just using those values, right? Did I accidentally delete that? Okay. What the hey? What the hey, man? Okay. So that just about does it for the init code. Let's take a look at this now. So what we want to do now is call setmin corner on our two voxels. So basically each voxel wants to sort of have the ability to be placed now into their correct location. You can see here that the spatial grid min corner is going to be slightly different because it has to use the extra occlusion radius there. So we know that that is something we actually stored. So that's solution atlas to spatial. So we know what the offset is supposed to be. It's supposed to be this. And so we know how to produce the corner when we have one and, you know, when we have one and then the other. We're going to want to be able to get the minimum corner here. So in this voxel grid, we want to be able to do something like this. So anyone who wants to work with the min corner can do that. So we're going to set the min corner by getting the min corner, you know, of the other one. So the atlas grid. And then we're going to subtract that offset. Like so. I do not know what's going on here. Forcoder's definitely having issues with the indentation today for whatever reason, which is unusual because I don't normally see a lot of that, but it's kind of weird. I might also do this. So let's do spatial min corner, and we'll just compute that like so. Yeah. And yeah. So that should be fine. So if I want to set the atlas grid's min corner and the spatial grid's min corner, I'll just do spatial min corner and atlas min corner. And I'm not sure what the hot voxel rect is actually for. I guess it's just to set the bounds. And you know, in this case, that stuff is probably stuff you would just get from the voxel normally, right? So, I mean, we can do it this way if we want to, but it's not really necessary to do it quite this way. So we probably want to streamline this a little bit. But either way, here's where that vox corner, this is the actual value we care about here. So the atlas min corner is this. And this value is actually just going to get done here automatically. So we really don't need to be doing that. But again, at the moment, I don't know that I actually want to touch that because there's just a lot of stuff going on here. So I think that's all good. In here, where we're doing our test work here, this stuff for the internal lighting core stuff. In this particular case where we've got the work, I don't know if we want to pass the work into the internal lighting core just so that we can sum it on the outside. That I really don't know. I suppose that's probably fine. Meaning the work array would be passed in here, but hard to say. Since the work count is kind of like computed in here, seems like a better place to do it. And since all you really want to do is take the summation of these things, it seems like the better idea would just be to pass the summation out so that this stuff is not happening in sort of arbitrary and weird ways, right? So if this is the actual summation that you're trying to take, like, you know, if this is what we're actually trying to do, then it seems like a smarter thing to do would just be like, instead of leaking this information out and having it be kind of, you know, unpleasant, right? I'm not even sure why we're quite doing it this way. There's a lot of weird stuff happening in here. We could clean a lot of this up. Yeah, so this should really look like this, right? And really what we should be doing here is saying, all right, this is doing a repeat where it's, you know, initializing these work things and sending them off, which it may do in a loop or it may not, right? And what I'm not sure about is why we did this. I guess the reason we did this is because if we don't have a queue, like calling in the external code, we don't want to do this, because otherwise you could just add the entries and then this would just work whether you were single-threaded or multi-threaded, right? So kind of annoying, but it's fine. So anyway, when this happens, then this will get summated, and then we'll end up being able to return that. So the only thing that I would say here is instead of this internal lighting core returning what it's returning now, what we can do instead is just take the work stuff here and make this be like a stat. And that way we can just, you know, return a lighting stats structure from this routine. And we can make this a little cleaner later, but for now, we can just do this. Right? So now that data will just come back automatically, and we don't have to deal with this weird like nonsense where we're returning out the work count and then like they're looping over stuff that they don't have necessarily. Like this, that was just dumb, right? Okay, so coming back to the way this was working before, so now we can just say, all right, the lighting stats come back through here in a nice clean way. We can then just use those stats directly as we were about to report them. So all of these are just stats dot, oops, right? And all of these are just stats dot. That seems like way better. Then in here where we're actually like lofting up these things in order to basically make stand-ins, we don't have to do this anymore, so we don't have to fake initialize the work structures. And furthermore, we don't have to do the computation after the fact, so this rolls up in there, which is actually great. That's way, way, way better. Because now we can just do lighting stats, and off we go. We can also just pull these out and then not touch the rest of the code if we want to, which also seems good. Okay, the KD nodes are going away. We're not going to touch that. And the table voxel dim stuff, again, don't care about any of that and shouldn't have to do that anymore, actually. So we'll probably have to call, no, we won't, because all this stuff will actually be in there. I guess it won't be because it won't quite be saved. So yeah, this stuff is going to be a little bit trickier. So yeah, one problem we're going to have a little bit here is calling the begin lighting thing. We may want to call the begin function and let it do what it's going to do. Like in other words, we may want to call begin. We may want to, instead of calling internal lighting core directly, we may want to actually call the full thing, right? And maybe like this collapses down into something that, you know, maybe this collapses down into one call anyway eventually. In fact, let's take a look at that. So here's another question. So the other question is just, yeah, so you can kind of see here. So the reason that we need, the reason that there's even a begin lighting call at all is because of the set light bounds thing. So the question is like, did we really need that to be the case? And I guess the thing is like, The reason that has to occur is just because if we don't call set light bounds, then the pixel shaders that operate in this part of the code, won't know how to look up their lighting in the voxel, right? That's the actual problem. And so that's the reason that this stuff is happening in here. But it seems like, we could just track the inputs to this and actually just let all of this stuff run. That would be a better way of testing this code, I think. Yeah, I mean, that would just be way better, right? And that way, we can just make this code be like run in its entirety. So I feel like internal lighting core can just be simplified into end lighting, and we can just call both of these. So, and what we do is so if you look at what would happen here, if you look at where the render group actually gets used in here, it's just to figure out what those basic values are. So it seems like it should be fairly straightforward to do, and it's a little bit of a bummer. Like, it does seem like maybe the set light bounds and enable lighting stuff maybe should happen kind of at one level above this. In other words, it would probably be nice to sort of separate these things out a little bit and not have them actually be retrieved directly from the game render commands, to keep this and the renderer separate, right? Because we're almost able to do that, and really all we need to know is the atlases that we're supposed to use. We don't really need anything else. And so if we were to move these things up, that seems really desirable to me. So I'm going to do that. So I think what we want here is like set lighting values or something. So these things here where we're calling into the group, so this stuff here, this is what we would actually do where we would set the lighting enabled up here, and then we'd actually make the calls in this. And similarly, like all of the stuff that was operating on the group would happen in here. So that way you'd have the render group in here and the lighting solution. You'd do these operations anytime you wanted them done, and you'd get the hot voxel rect. You'd actually get that in here instead, right? And yeah. So in here, what we'd do is we'd say, okay, we can get these things. We actually know we can get the total bounds by just looking at the atlas itself. So at the atlas grid, we could just say, what's the total bounds? That's that box. We already know what that is. And then in order to get the actual dimension of it, because we need the inverse dim, we can just say get the dimension of the hot voxel rect, and then we're done, right? So this can be a self-contained function, and we don't actually need, I'm surprised that compiled, we don't actually need the render group anywhere. So then in here, where we look at what we actually needed the commands for, you can see that basically what we need is we just need the two atlases. So what this actually should be doing here, instead of passing the render group at all, is it should probably be passing more specifically. It probably would need to pass the two atlases. So we would have one lighting atlas. It's the spec atlas, one atlas, that's the diffuse atlas. And so these are the two lighting atlases that the renderer is using, and this will update them. So then you wouldn't need the game render commands. You could just look at the spec atlas. And then down here where you actually have to operate on those, you just do. I think that's what we would want. So now that's kind of like, you know, separated out, and you need to call both of these things, right? So you need to call begin lighting computation because you need to be able to, you know, figure out where things are going to be. And really, it's not begin lighting computation. That's probably a misnomer, right? It's really like setting the location of it. So what you're really doing is saying more like set lighting region or something, or like compute lighting region, or change lighting region, update lighting region. I don't know what you want, what it would be called. Set lighting region bounds. I don't know. So really what we're doing here is we're doing something more like this, which is like setting up, you know, set up lighting region and like, you know, push lighting render values or something like this. These are not good names, but I'm not sure how you actually describe what's happening here. One is setting up sort of where lighting is happening, right? And the other is actually telling the renderer what it needs to know. So this is just saying where the lighting is going to happen. We've got the render group, and this where we're pulling out those lighting values in here, right? So it's really this process where we need to be able to send those things. So we need to be able to say, here's the diffuse atlas and here's the spec atlas, right? And we need to send those down because the lighting region needs to know about them, unfortunately. So I'm not sure what this is complaining about. Is the render group a pointer? Yes, it is. So getting closer to good, still not entirely fabulous, you know, but better. And then for end lighting computation, you know, this has sort of the debug output, which could be split into a separate path. And the diffuse atlas and spec atlas here could be passed again or could be cached. And I assume that maybe the right thing to do is to actually cache those values when you set up the lighting region, because they can't change. Like, it would be very bad if you switched which ones they were in the middle of that. So yeah, like, hard to say. But anyway, when we do the end lighting computation in here, just taking a look at what's happening, this debug stuff could definitely be in a separate piece. It doesn't need to be in there at the moment. So I'd also say maybe we could have like push lighting debug values is a separate thing. And that way, anything that was operating kind of on, you know, debug information and pushing that out to the renderer can be done in a separate place as well. So basically, like, push loading debug values, oops, would be a separate thing. I don't know where the end loading computation is. There it is. So in here we'd say, like, yeah, okay. That's a separate thing you can do if you want the debug stuff to happen, but it's not entirely necessary. And I'm not sure where the setup part comes in. Does this actually use that? It doesn't, so that isn't really necessary. And again, the diffuse atlas and speckle atlas, I guess for now I'll pass them in, but we should like see what we actually want to do about that, because I'm not entirely sure. Maybe those just get cached. Those are things that are kind of, that bridge two systems. And so it's always a little bit delicate when you have a situation like that. And as we're starting to clean this code up, it's something we can think about how we really want to do that. So instead of end lighting computation, I'm going to call this update lighting, because that's what it actually is. And off we go. So now we shouldn't need the commands anymore here. In terms of the boxes that get passed through, this stuff is now part of like where we're actually doing the, yeah, like all of this stuff where we have the boxes that come through here. That should actually be, what gets passed to update lighting, right? So these bits here, yeah. So these bits here where we say update lighting, so we say set the render region above, and then we say, hey, update the lighting for this set of occluders and all that stuff, right? And I think that's more or less how that has to go. I don't think there's any other way. It's kind of nasty, but you have this like split problem where you want things to be flowing in a particular way, and I don't think there's any other way to do it. Okay, so you get the two atlases, and then you get the occluder count, and the, what are these, lighting box, and the occluders. You know, for now we're storing these, but I'm not sure they really should be in there. So as we clean this up, those may go away as well. So there's the occluder count. In this case, render group, it's never just called a group. There we go. And it looks like the platform lighting queue for some reason didn't get moved down to where I actually wanted it in the parameter list, which was there. All right. So I think that's good. This is starting to get more towards good. I think that's much better. So I think these functions at least now properly reflect what they do, which is good. Now we've got a bunch of work left to do. We'll pick it up tomorrow. We can go to a brief Q&A for a few minutes, but we're already over time, so I'll keep it pretty brief. Anyone have any on-topic questions? Oh, yeah, so we kind of didn't finish that code yet, unfortunately, that you're talking about there with the Atlas min corner. So I can kind of button it up a little bit now, but we kind of need to do it a little bit differently. So this part is probably fine because these will be set to 0 initially. And then when we move through here, yeah, you're right. So we just want to use Atlas min corner here. Like so. Thanks for that catch. That saves us the trouble of finding it tomorrow. I think that's probably correct now. Insobot. That was very good, Insobot. Yeah, so the reason that 603 and 604 are not on YouTube yet, so 601 and 602 is because OBS is amazing and messed up the recording on one of them, and I have to like go extract it from the Twitch stream properly. So, yeah. OBS is a real treasure. I mean, you get what you pay for, right? Max node max node index doesn't exist anymore. But I know where you're talking about. You're talking about this? Is this the part you're talking about? Was the assert inbounds this part? I'm not sure I know exactly what people are asking here, so you'll have to tell me. I think both pieces of code that you're talking about are now on the screen, so I'm not sure. It's missing the grid pointer. You know, you're right. Oh. How long have we left it like that? Unbelievable. That's a bit of an owl of shame there. So, hey, now we have our asserts back. They were turned off there for a minute. I was like, how was that compiling? That's how it was compiling. Yeah. So another thing I should do before we go any further is I'm going to delete the lighting record that we had. So in Handmade debug, we've got all these dumps. I'm going to delete those because they're wrong now. So we're going to want to recapture and retest everything tomorrow, starting from scratch, right? So I'm just going to get those out of there real quick. All right. We'll pick this up tomorrow. Okay, thank you everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so that you can follow along. There's a whole bunch of like debugging and streamlining work that we're doing right now, so it's totally stuff that you could try if you're looking for something to practice at home. That's what I'll be doing tomorrow, and you can try it tonight and see how far you get. That's it for today. I'll be back here tomorrow. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.